right, checking with the people online. Can you type yes? You can hear me for those. Okay, thank you. And you're also saying the OneNote. Right. Okay, good. So then it's all set. Okay, good evening. Let's get started. And then we can get on with our waking life. All right, let's continue on a vector function. And we just started the derivative vector function. Okay, we'll learn a little bit about integrals and a few more concepts. Okay. Vector function, as the keyword said, it's a function, and but also a vector at the same time. With a different t-value, you get a different vectors, right? That's why it's called a vector function. A derivative vector function, okay, there's a formal definition, but in reality, when we do, if the vector function is given, when you take derivative of it, you're going to take derivative of each component of the vector function. So that's very simple. Just like derivatives of a single function, okay? You do have very similar so-called product rule. So in this case, our product is a vector product. So vector product means could be dot product. It could also be cross product. So you can apply the product rule to either dot product, cross product, similar to what you have done to the scalar function. Right? So product rule says the dot product, you take the derivative first one, and then dot v of t, and then u of t dot the derivative of the second one. That's essentially, instead of a scalar multiplication, right? Now you have a dot product, vector multiplication. The second one is exactly the same thing, except you replace the dot with cross. So I'm not going to go into details, and this is basically not much of a difference, except you're doing dot product or cross product. Okay. So I'm going to show you a couple more things, okay, that's particularly will be useful actually. So the first thing I want to show you, I will make use of the results of this example right here. Okay. All right. So let's consider ourselves a vector function. So let's say given a vector function. Okay. Given a vector function, this is a special function. Okay. This is a function of a constant length. It's not any arbitrary vector function, but its length is constant. So let's suppose if the vector function is represented using r of a t, then a constant length means if you take the absolute value of this vector function, then you're supposed to get a constant c. C is constant. Okay, so vector could be changing. So vector at a different time could be pointing to different directions, but its length is maintained at a constant value. That's what this means. So I can add a square here, it's the same thing, still a constant. Okay. And as a matter of fact, I will make use of this. So what would be a constant, a vector of a constant length? What will be an example of that? You actually have seen this before. So say, for example, okay, if you have a circle in XY plane, And then you have a point on the circle, and that point is moving around the circle at a constant, let's say, velocity or speed. Okay. So basically, if this is a position vector here, it's position vector, and then when you take the derivative of the position vector, you get dr over dt. So this is essentially a constant, a vector of a constant length. Okay. Angular constant speed. All right. So now let's look at, for this case here, right? I'm gonna present a result and then also present a relationship. Okay. All right. So first of all, get back to this equation here. Okay, so this length square equal to a constant. Okay. If you recall in the first lecture, or maybe a second lecture, so when we do the review, right, the length of a vector, okay, square, is actually the same as when you write it as r dot itself. Okay, so if you have a vector and you do the dot product of itself, then you get the length square. Okay, very easily you can verify. For example, if you have vector ABC, for example, right? ABC dot itself, you get a square plus b square equal to c square plus c square. Okay, and this is what this is basically the same as, right? It's absolute value, a square plus b square plus c square, and then square. Okay. So this is a conclusion basically. Okay, so your length of the vector square is equivalent to the dot product of itself. Good. Okay. Of course, now we know in this case the length square is c squared. Okay. Then I'm going to do is I'm going to take a derivative of both sides of the equation with respect to t. Okay. So we're going to take a derivative of this with respect to t, and of course equivalent to take derivative of the dot product of itself. And you're taking derivatives, so you had to take derivative both sides. So the right side, you're also taking derivative. Okay. Apply same action. And the right side, it's a constant. So the derivative of that is 0, right? Yeah. So then our left with, we deal with the left side. Okay. So deal with the left side, I'm going to look at this term. So we're taking derivative of a dot product. So what do? We apply the product rule, right? We just learned the product rule. So let's apply the product rule right here. That means r prime of t dot r of t plus r of t dot r prime of t equal to 0. And these two are literally the same. So a dot b equal to b dot a. And essentially you get 2 r of t dot r prime of t. Now this time I'm going to write it back to this notation. So this sometimes this notation looks better, equal to 0. So 2 times something equal to 0. So then you don't really need a 2 here, right? Basically, we have r dot derivative r equal to 0. So this results, don't remember this results, it's based on a condition given at the beginning, which is the vector function has a constant length. So when the two vectors are dot each other, when they dot each other equal to 0, that means what? The two vectors are what? Perpendicular, right? Excellent. So this is basically a conclusion that we're going to actually to make use of. When you have a vector that's a constant length, right? You see here, this position vector, that's constant length, right? So it doesn't matter where the point is on this circle, its position vector is always a constant. The length of position vector is always constant. Okay. And if you take derivative of this, okay, if you take derivative of the position vector, and you get the velocity vector. So in this case, we can safely conclude the velocity vector is actually perpendicular to the position vector. It's all because this vector is a constant length. Okay, so that's the conclusion. It's actually a very important conclusion, right? So I need you to firmly remember, this is not arbitrary results, okay? This is results, of course, has to have a certain constraints or restrictions attached to this. Okay. So we'll leave it for this for now, and then we're probably going to come back to this condition later when I introduce you tangent vector, normal vector, and binormal vector, because there are a few important vectors I want to show you. Any questions so far for this particular example? Good. Okay. Okay. So we talked about derivative now. I want to show you integral action of a vector function. Of course, as you're going to see, this is really nothing new, right? As long as you understand what integral is, and you can naturally understand what integral vector function is. Okay. So we'll use the same notation for the vector function. So if you have a vector function given, and then if you're going to integrate this vector function, so what you do is you essentially integrate each component of the vector function. Okay. That's what you do essentially. Okay. Okay, but there's just one little thing I need to bring into your attention. All right. So if you recall, if I integrate a scalar function, I can get its so-called antiderivative, right, f of x. And because this is an indefinite integral, so we usually should plus a constant c, right? That's what you learn in first year. Now we're learning vector integrals, right? So, I mean, first of all, let's say this is antiderivative. Okay, so what if I have the counterpart of antiderivative for this vector function? So I'm using capital R of t, okay, to represent this is the antiderivative, okay, for R of t. Okay. So if this capital R of t is the antiderivative of the vector function R of t, then if we integrate this with an indefinite integral, okay, so that should give me this antiderivative. Okay, so this is where the pitfall is. What should I do? What should I add? Should I add a c? Yes. Sorry, louder. Plus xyz. Now the XYZ. So you definitely, and you all understand why you have a C here, because when you take a derivative of the left side, C is gone, right? Yes. Vector, exactly, right? You need a vector here, not just a constant, okay? So you need a constant vector at here. So that's just a very little pitfalls, but it usually, you know, it doesn't really matter to us because most of the time we'll have a integral limits given, so you won't be bothered by a constant C. But however, you need to understand the difference, right? What is the difference between the constant, a scalar function integral and the vector function integral? Okay. Good. So it's that simple. When you deal with integrals of vector function, right, you just have to deal with integrals of each component, and you put them together, you get the resulted integral. Okay, any question? Okay. So what I really wanted to also to talk about today is a few unique vectors, okay? Unique vectors that that's particularly interest to us. And those vectors are also very common to be seen in physics or in dynamics. So the name of the vector, write down the name of the vector. So tangent vector, unit tangent vector, okay? And unit normal vector. So maybe I should add another one. So normal vector, and then unit normal vector. Okay, so there are 4 different things, but the unit ones are probably more interesting to us. Okay. So what's tangent vector? So again, let's say consider, I'm going to start from the beginning. Consider a vector function R of t. We have used this for many times. Okay, so let me draw a diagram here. If this is curve C, this is a point, then R of t is the position vector, right, at that particular point, for that particular point. Okay, so first is the tangent vector. Okay. So tangent vector is very straightforward. We have already shown, as a matter of fact, is basically you take the derivative of this position vector and you get the tangent vector. Okay, so this is a tangent vector. So why is it called a tangent vector? It's because if you take the derivative of this position vector and then the resulted vector here is a vector tangent to the curve C. And that's why it's called tangent vector. Okay, so that's very straightforward. So now the second one, right, is a unit tangent vector. And this is also very simple. So if you have a tangent vector, so then what all you need to do, okay, all you need to do is to normalize it and you get the unit tangent vector. And you can certainly write this whole thing together. So I don't think anybody should have any problem with this tangent vector and unit tangent vector, right? What comes next may require a little bit understanding, right? All right, so the next one is what we're going to talk about is it's normal vector and unit normal vector. Okay. So more precisely, we call it principal unit normal vector. So let's call it number 3 here. All right, so how do we get to this so-called principal unit normal vector? Okay, so we start from this t hat. So you start from this t hat here. Okay. So t hat, go back to number 2, is the unit tangent vector. Or it's a vector that has what? Unit length, right? Has unit length. So which means its length is 1, or in other words, the length of the vector is a constant. If the length of the vector is constant, then by making use of the results of the previous example, I have dt hat dot t. Okay, so this is all function of time. So the dot product, according to the previous results, should be, what should it be? 0, right? Because the length is constant. In other words, this t hat is perpendicular to dt hat over dt. Good. Yeah. So basically, if I have a drawing over here, then if this is a t, t is pointing in the same direction of t hat, then dt hat over dt will be a vector that's actually perpendicular. The drawings is not that great. So this dt hat over dt is a vector perpendicular to the t hat. Okay. And this is not the final results we're looking for yet. So what we're going to do is, okay, we're going to define this n here, call it the dt over dt. Okay, so dt hat over dt. This n here, okay, this is called a normal vector. Okay, it's not the uninormal vector yet. Okay, so this is a very common mistake because when people say, oh, you're taking derivative of a unit vector, does that give you a unit vector naturally? The answer is no. Okay, so derivative of unit vector doesn't necessarily give you a unit vector. As a matter of fact, in most of the cases, it doesn't give you a unit vector. Okay, so we call this as the normal vector. Yeah. So the normal vector, of course, this n is perpendicular to this t hat. That's how our definition is. Now, if I have to go a little bit more step here, and I can introduce using the limit concept for derivative. So basically this normal vector, right? If I use the limit notation, is what? It's defined by this limit notation. Okay. So why am I doing this? I'm trying to illustrate a little bit here. Okay, so let's understand a little bit about this normal vector. Okay, so let's say I have a curve like this. Then at a particular location, I'm going to draw the t hat. So this is t hat t, tangent to the curve C. And then after a little bit of time, you're at this location, and then you have t hat t plus delta t. Okay. So these two vectors, right? According to the limit here, you're subtracting the t hat from t hat t plus delta t. So I'm going to basically put these two vectors together into a triangle. So let's draw it here, and maybe we can draw it here. Okay. Make the triangle here. I'm going to move this vectors free, right? So I'm going to move the vector parallel to the beginning of this point here. Okay. So basically, it's like this. You have a t hat over here, And then you have t hat t plus delta t here. Right? So these two vectors. So I'm moving the two vectors to start from the same location, right? So that I can do the subtraction. And now you can see, if I use t hat t plus delta t minus t hat, what is the results? It's this, right? It's the red one. Right? And of course, where t is going to 0, meaning the two vectors are getting, right, pretty much close to starting from the beginning. So basically, okay, you at this location, and when you do this integral, when you do the limit at here, or when you do this derivative, the n here, right, resulted in, so this is basically your n and here, right, your n, the direction. So this is the n direction here. And the n is called the normal vector, and because n is normal to the t hat. And what's also more information given by the n is, so this n, it gives you the information of a so-called the direction of curving. So direction of curving. So if you have a curve, right, and how do I know is a curve going to curve to this direction or curving to this direction? How do I get that information? I can look at the vector n here, right, to tell me this direction of curving. So the direction of this n give me this information. So direction of n, right? So I guess, how do we represent a vector's direction? So we normalize it, right, to get its direction. So this is the so-called principal unit normal vector, okay? So now we have the n hat, which is the normalized version of n. And we have n, which is dt over dt hat over dt, and then divided by its length. Okay, so you got these two vectors, right? Basically, I end up with two very important vectors. One is called t, another one called n hat. Okay, so t hat is a unit tangent vector. And unit tangent vector basically give us the direction of velocity. And n hat, as we have just discussed, give us the direction of turning or curving. So these two vectors, and they are perpendicular to each other, of course. So in your head, if I have a question and ask you to give you a vector function and asking you to present the unit tangent vector and unit normal vector. So what do? You have to get the tangent vector first, and then you normalize, then you get the unit tangent vector. Then you take the derivative of unit tangent vector to get the normal vector. Then you normalize it to get the unit normal vector. So that's the procedure. And the last step usually is so sometimes, as I said, some students just think this is an n hat, right, instead of normalizing it. So what's even better, so just one more step at here, you can create the third vector by doing the cross product of t hat and n hat. And then by doing this, you create a so-called binormal vector. Okay. So the three things, T and B, okay, they're very useful actually. So now you have T and B together, you can create so-called T and B frame, a coordinate frame. So let's say, for example, right? Let's see if I have a curve, okay, in 3D space, then if this is a tangent vector, this is the uninormal vector. Then according to this notation of how the binomial vector is created, it's a T cross N. So where would that be pointing to? T cross N, right-hand rule. Yeah, so it's pointing down, right? So it's pointing down as a B hat. Okay. So this frame, you see this frame I just draw here, the three vectors, T and B, they're basically like what? What does it remind you? A coordinate system has I hat, G hat, and K hat, right? So this is basically like I hat, K hat, G hat. But of course, you're already giving a reference frame of X, Y, Z. Your I hat, G hat, K hat doesn't move, right? It's because reference frame. But this frame, if you look at this frame, it's literally a moving frame because you go to a different location in the curve, and that frame will also change, right? And the vectors T and B will also change. So this frame is a moving frame along this curve C. Okay, yeah. I actually have a video. I'm not sure if I have time to. So maybe I don't have time to do that. But anyway, so let me find it. Maybe the next lecture I can show you. So basically, you know, one of the application, right, in robotics is, as you all know, you have seen the robotic arm, and the robotic arm typically has a hand attached. We call the end effector attached at the end of the robotic arm. Okay? And then you require the robotic arm to perform certain kind of a task. So very common task is you want the arm to lift something and then place somewhere, or even massage this object, right? So there's a critical information basically is, how do I orient my end effector of the robotic arm to touch this object? Okay, so it's all, of course, it's up to the end user how to define it. But how do you basically reference that information, right, to this given object? The one way to do that is you create this TNB frame. Okay, you have a TNB frame attached to the end of this robotic arm. And then you orient this frame, okay, you orient the frame to line it maybe with, for example, another frame on the surface of the object. So if you think of the surface object, you can also always create another frame, like a TNB frame. Then you can align these two frames together as an indirect information how the arm is supposed to approach this object. Right? So that's the information, how you align this together. And same thing, sometimes there's a camera. There's a camera attached somewhere else, and the camera has a feedback information to the robot. And that feedback information contains most probably also this TNB frame to serve as a so-called orientation information. Right? So not just the position information, you also have you need an orientation information to properly touch something or manipulate to handle something. Okay? So this TNB frame is very simple to obtain, but it's very useful in many applications. Okay? So if I can run an application next lecture, I'll show you. So my requirement, of course, is for you is, right, here is more of a review of your derivative skill. Okay, so let me show you one example here. So let's say I have a vector function, t squared, 3t, and 5. Okay. I want you to find out t hat and n hat. Now, this probably seemingly to be a very simple question, but according to my experience, I've seen some students struggling with the derivative action. So first couple steps typically is okay, but when it comes to the n hat, and that's where things can get a little bit messy. So first, let's see. We calculate the derivative of r to give us the tangent vector. So that's pretty simple. We got 2t30. Then we normalized it to give us the unit tangent vector. So that gave us, right, 1 over 4t squared plus 9, 2t30. Okay, so these two steps, 100%, I think everybody would be able to got that. Okay, so this is the next couple steps. So now time to get the unit normal vector. To get the unit normal vector, I need to get this normal vector first, which is dt hat over dt. So this step here, what do you need to do? You need to take derivative of each component of this t hat vector. And each component, the first component is 2t. Okay, so basically you're taking derivative of this vector here. Second is 3 plus 1, 0. All right, so now this is where I need you to, if you're having trouble doing this kind of derivative, I need you to actually just bring out your first year textbook or just practice a little bit, okay? So, technically speaking, in order to get a derivative, I need to take a derivative each term. So I'm gonna only try to demonstrate what will be the derivative of the first term. So then you're looking at, let's just write down the derivative first term here. All right. Okay, so then time to ask yourself, can you write down, can you calculate the derivative of this sort of a fraction terms, right? So trust me, I've seen many people struggle even in the second year in this course, right? So bottom line is, the point here is you have this quotient rule, okay? So u over v is u prime v minus v prime u, and then v squared. And you could also actually use product rule. So 2t over this is equivalent to 2t times the 4t squared plus 9 to the power of a -1 over 2, right? So you can consider this is a product, two terms. You can also use product rule, but you can also use quotient rule, right? So due to the class time, I'm not gonna show you all the details how to do this, but however, I strongly recommend if you're not comfortable with the product rule, with these kind of things, do practice, right? So I'll just quickly write down this using product rule. So the bottom is a v, so v squared give me 4t squared plus 9. And then u prime v, u prime is 2t, give me 2. So 2 times v, and then v prime u, okay? So v prime u, so v prime, v is the bottom term, so which is 4t squared plus 9 to the power of 1/2. So then its derivative give me 1/2, right? 4t squared plus 9, and then the 1/2 minus 2, so 1/2 become -1/2. And then you have to, it's a chain rule here, right? And you have a 4t squared plus 9, then you take a derivative of the inside the bracket, the term inside the bracket, which is at. Okay. So that is v prime, n times u, and times 2t. Okay. So time to ask the question here. So are you feeling comfortable, right, with this part here? Because I do know every year there are students struggling with this portion. Okay. Any questions? Okay, good. So once you get this step, okay, and once you get this, I have seen even more struggling to the next step, which is to simplify the situation, okay, to simplify it. And I see a lot of students just leave it, that's it, give it to you, you know. Although technically, you know, if you got everything over here, you got it right. But if you cannot proceed to the next step, then you won't be able to write down this n hat properly. Okay? So next step is you need to simplify things, okay? So to simplify this, of course, what you need to do is this is AT times 2T. It has 1/2 here, so there's some simplifications, right? 1/2 cancel the 2, so you only have AT and here. Okay? So for this term, basically this term here, let's put the AT here. So this term you need to write it into this way, okay? Or yeah. Okay. Right, so because it is negative. And then divided by what? 4t squared plus 9. Right. Is everybody following me here? Yeah, good. Okay, so now do the fraction simplification. So this is a minus something over something here. So how do I simplify this? So 2 times this denominator. Of course, they are both square roots. So 2 times 4t squared plus 9. Okay, so when you use this times this, you get this, and then minus AT. Did I miss the t? Sorry, I missed the t here, right? T times t is square here. Yeah, and then AT squared. So, and then divided by 4t squared over 9, last term, and then divided by 4t squared plus 9. Okay. So finally, right? This is actually something when I teach my kids in high school, right? I keep telling her many times, A over B over C over D. What is that? A times C over B times D. Okay, yeah. And trust me, they always hesitate, you know, they always hesitate. So this is A over B and over C. So what should have? So simplify this first. 2 times 4t squared cancel the AT squared. So you only end up with 18. And then bottom here, you have this times this, which is 4t squared plus 9 to the power of 3 over 2. Okay, and that's how the final simplification should look like. Okay, so that's exactly my point. You probably should be okay. Most people okay here, but then from here to here, there's a bit of struggle I can see sometimes. Okay, so now you get the derivative of this term, and you can try to get the derivative of this term yourself. All right, yeah, but I can write it down for you. Negative 12t over 4t squared plus 9, 3 over 2, same denominator. So do practice and make sure this is very, very proficient, okay, when you see this kind of question. All right, once you get this, basically what we got the n at here, right? We got the n, okay? So we need to calculate n hat, meaning you have to calculate n over the magnitude. Okay, so you need to put things together. I mean, you have, so what do I have here? I have this term here, I have this term here, and the last term is 0, right? Last term is 0. So you're using your calculus magnitude. So magnitude is square of this plus the square of this, and then square root, okay? And then you use the original vector divided by this. Okay, so you end up with a 640 squared plus 9. Sorry, this is this one here. Sorry, this n has absolute value equal to 6 over 40 squared plus 9. Okay. Then you use your vector divided by its magnitude. So you're going to have these results at here. Perhaps you get. So none of this is a part of this course, okay? So I would encourage you to practice the computation. This is really nothing new at here. To me, I mean, I don't think it's a difficult one. It's just you have to be very detailed to not make any mistake. So finally, I mean, you can always verify, is t hat times n hat equal to 0, right? That's how you can verify whether your results is right or not. And of course, it will be 0, okay? So that's how you can get your t hat and n hat. If there's one more step, what's the b hat? And then you do the cross product. It's a little even messier, but yeah. So you can use computer to help you with that, but in an exam, I think up to n hat, that will be enough. Okay, yeah. Any questions on this subject? Okay. Yes. How this bottom comes from, right? Yeah. So as I said, you know, the square of this, let me see, how did you? Yeah. Yeah, you can definitely verify. So you're saying how this is obtained, right? Basically.
No, that's fine. Just the next bit going down. Yeah.
Over here. Oh, well, then you are, well, okay. Maybe, let me write down the n here. So n is 18 over 4t squared plus 9, 3 over 2. Negative 12t over 4t squared plus 9, 3 over 2, and 0, right? Yeah. So basically, you are going to divide this vector with this vector. Okay. So now you can see when you divide this vector, so that 4t squared plus 9 flipped, right? And then you'll try to cancel the bottom from the bottom here. And that's how you end up with just a square root term right here. Yeah. Okay. You do need to, I skipped a few steps, but yes. Sorry, louder. How did I get this one here? Yeah. I mean, I did skip the step here. So basically, you need to square this term plus the square of this term, and then square root, which should give you this one here. Try it out, okay? Yeah. Okay. Almost running out of time, but for the benefit of the assignments, I just want to quickly mention a little bit of symbolic concepts. Okay. All right. So let's say I have a if I have a 3D curve, okay, given in terms of parameter theta, right? So this is a little bit different, right? We usually write down the curve in terms of t, but this time we write it down using theta. And this curve is actually a so-called Lissajous curve. If you have been to an amusement park, you must have played those roller coasters. Roller coasters are designed actually based on this so-called Lissajous curves. So it's if you plot this, part of the curve can be used to construct a roller coaster. Okay, so theta here, often in time, is a function of t. So then if you plug the theta, we're not writing what it's in general. Maybe it's a t square, maybe it's whatever, t, right? If you plug the theta over here, then your r will eventually become a function of t. But the point here is, you may be interested in, okay, what is the velocity, right? What is the velocity of this roller coaster? So of course, you want to take a derivative r over t, right? But of course, but then this function here is not directly given in terms of t. So what you do is, it's very straightforward. You're using a so-called a chain rule, right? So what you do, you take dr over d theta first, and then d theta over dt, right? That's a chain rule. So d theta over dt, we don't know what the theta is yet, so you could just write it as a theta dot, right? Temporarily indicate what d theta over d. This is essentially called a symbolic calculation. You're keeping the theta in here. Then what is dr over d theta? That's pretty straightforward. You got three terms at here. Then you just calculate the derivative for each one of the term, cosine theta, 2 cosine theta, and then negative sine theta. The whole thing multiplied by theta dot. So that would be your velocity of this roller coaster. If you have a theta, then you plug it in, you get the actual velocity. Okay, so I just want to quickly point this out because there's one assignment which I'll give it out actually today. Yeah, well, I'll give it out today, and then you have some idea. Oh, by the way, okay, we're gonna have our first quiz on next Friday. Okay, and we'll give you 48 hours to do it. So basically, the quiz will be released, say, in the midnight of a Friday. Okay, actually midnight of Thursday. And then you have 48 hours until Saturday to do it, because that's taking everything into consideration. You might have classes, but you only have 1 hour to finish though. So you can, once you start, you have 1 hour, you get one question as a long answer, and then there's two very simple multiple choice question. Okay, you're free to work with each other. You're free to look at everything, but just be careful. Each questions you get may have a different numbers of values from your peer. So you got to work on you, and don't jot down your friends, which is completely different from yours. All right. Yeah, that'll be a huge trouble. Yes, go ahead. The question designed, actually in a normal situation, 20 to 30 minutes, you should be able to finish. But because this is a quiz, I'm giving you definitely enough time to do it. Yes. Let me stop this first.
Professor, can we ask questions before you close the Zoom meeting?